Howdy everyone, my name is Michael Troy and I'm the O-REU undergraduate researcher from Texas A&M University for the project Identifying Latent Variables for Describing Atmospheric Profiles Used in Aircraft Geometry Optimization for Sonic Boom Reduction. I'd like to say a quick thank you to everyone involved in this project as well as all of the sponsors and collaborators that made this project and overall experience possible. The overall scope of the NASA ULI research is to reduce the perceived loudness of sonic booms through shape morphing aircrafts. In 1973, supersonic flight was restricted since sonic booms were a nuisance to the public. Now, only supersonic flight over water is allowed, which increases the distance needed to be traveled, resulting in greater fuel consumption and greater operation costs. The objective of this project is to aid in pre-computing optimal morphed aircraft geometries to help reduce sonic boom loudness. In order to do so, one aspect of the problem is that the outer mode line of the aircraft, or shape, needs to optimally morph to all possible atmospheric conditions. My research is focused on representing high-dimensional atmospheric profiles in only a few dimensions, or latent variables, to enable optimization of the aircraft in a reasonable amount of time. This can be achieved by using an autoencoder, a neural network-based machine learning technique. An atmospheric profile consists of data points collected at varying heights across many different locations and times from weather balloons. These data points consist of important atmospheric conditions such as temperature, relative humidity, and many more at their respective height above ground intervals. These conditions affect the loudness of a sonic boom that propagates through this atmosphere before eventually reaching the ground. Some preliminary studies were performed to understand and determine important atmospheric conditions to help with optimization of the autoencoder. One technique being used is Python clustering algorithms, which find similarities among data points, in this case atmospheric profiles, and clusters them together. There are two main clustering algorithms I worked with. K-means is based on the distance from centers that were calculated from the data, while dbScan clusters points based on how close points are together. As you can see in this image on the left, depending on which algorithm you use, there are a set of points that will be a part of a different cluster. The downside of K-means is that the user has to specify the amount of clusters, essentially splitting the data sometimes by force. The reason this technique was used was to determine important atmospheric conditions that would prove to be useful in later reconstructing the original atmospheric profile, done using an autoencoder. A neural network regression model was also used in helping determine important atmospheric conditions that would prove useful later on. The purpose of the regression model was to take an atmospheric profile and try to predict what the perceived loudness value was by finding similarities and differences in a large set of atmospheric profiles and applying that learned knowledge to a specific set of test profiles. The preliminary studies performed resulted in some information that proved useful in optimization of the autoencoder. These are referred to as features, which are values derived from the rest of the dataset, such as average temperature. Now, what is an autoencoder? An autoencoder is a form of unsupervised machine learning that takes in data, in this case it's an atmospheric profile, it then compresses it down, then attempts to recreate the original data from the compressed representation with as high an accuracy as possible. It is mainly being used for dimension reduction since a single atmospheric profile is composed of many dimensions. The autoencoder model trains on a portion of the data, at the same time validating itself on another portion of the data. The model does this because we want the model to perform well on data that it hasn't been exposed to yet. The main reason this technique is being used is to make optimization of the outer mode line of the aircraft less time consuming. Because a single atmospheric profile is represented by many dimensions or data points, it is difficult to optimize over all variations of all of these dimensions, especially when all of these variations may not be feasible. By reducing the amount of dimensions a profile has while still retaining an accurate representation of the original data, optimization of the outer mode line can be made more efficient since there are less dimensions to account for. Currently, the autoencoder is able to reduce an atmospheric profile from 154 dimensions down to 6 while still retaining a lot of the original information. The core question, however, is how few latent variables can we have without sacrificing too much accuracy? Here's the exact autoencoder architecture that was used. The model takes the input, which is an atmospheric profile of 154 dimensions, then expands it to many dimensions before compressing it down to the amount of wanted latent variables. The model is symmetrical, so it then rebuilds the atmospheric profile from the compressed representation in the same steps but in reverse order. The activation function's purpose in each layer is to help the model learn patterns in the data. The autoencoder repeats this process on many atmospheric profiles to learn as much as it can in order to help in its predictions. Here's a comparison of true temperature and relative humidity plots as a function of altitude with their predicted counterparts for a single atmospheric profile. The red curves represent the predicted profiles and the green curves represent the true profiles. As you can see, the autoencoder does a good job of recreating the original data even after the original data was compressed. Here's another comparison of a different atmospheric profile with less accurate results. One way to address this problem is by running these predicted profiles through S-boom and PYLDB, which are algorithms that propagate a sonic boom through a given atmosphere and produce a perceived loudness value. If the perceived loudness value is close to the true profile perceived loudness value, then this can be an indicator that the predicted profile may still be valid, though it may not visually seem so. Here's the process I went through for determining the perceived loudness error between the true and predicted profiles. First, the true profiles are run through the autoencoder to produce a predicted version of that atmospheric profile. Then, both the true and predicted profiles are run through S-boom and PYLDB to produce their respective perceived loudness values. These values can then be compared to see how well the autoencoder performed. Here are the temperature and relative humidity plots for the same atmospheric profile, but the predicted profiles were reconstructed from varying amounts of latent variables. From a visual standpoint, it can be seen that the fewer latent variables that the algorithm has to reconstruct the original data from, the more trouble the algorithm has doing so. This makes sense because the algorithm is trying to recreate a large set of data with even less information. For the 6 latent variable autoencoder, here are some plots showing the errors in the true versus predicted profiles and perceived loudness values. On the left, there are histograms that show the frequency and profile prediction error using the error metric of root mean squared error. While there is still error in the profile predictions, it is to be expected when reconstructing many dimensions from only a few. On the right, there is a histogram showing the absolute error between the perceived loudness values of the true profile versus the predicted profile produced by the autoencoder. This was done, as previously mentioned, by running the predicted profiles through algorithms that propagate a sonic boom through a given atmosphere and give a perceived loudness value. The majority of the predictions have low error, but the spread can be narrowed down by optimizing the autoencoder to produce more accurate results with possibly even having fewer latent variables. Here are some plots that show the root mean squared error as a function of height above ground when comparing the true and predicted values. At lower height above grounds, the autoencoder struggles with predicting the correct values, shown by the high error, which is something worth looking at in the future. Now, what exactly happens when the amount of latent variables is reduced? Earlier, we saw that the predictions were less accurate, at least visually. From this plot, we see that for the 4 latent variable autoencoder, around 61% of perceived loudness values produced by the predicted atmospheric profiles were in a reasonable error range. Now let's compare that with a 3 latent variable autoencoder. From this plot, we see that for the 3 latent variable autoencoder, around 66% of perceived loudness values produced by the predicted atmospheric profiles were in a reasonable error range. It is expected that the fewer latent variables you are reconstructing an atmospheric profile from, the more difficulty the autoencoder has with the reconstruction process. However, these results go against that expectation, which is something to also look into in the future. Here's a table summarizing the errors from the different amount of latent variable autoencoders. I would recommend sticking with the 6 latent variable autoencoder due to the dimension reduction and retention of an accurate representation of the original profile. The fewer latent variable autoencoders begin seeing much more error, which is expected. Based on my work for the summer, the autoencoder model that was created is able to allow significant dimension reduction of atmospheric profiles in exchange for small sacrifices in accuracy. Out of all the model architectures I tried, I found that expanding the data, then compressing it down to 6 latent variables worked very well. Some improvements that can be made are on the optimization of the autoencoder. By reducing the compressed profile representation to as few dimensions as possible while still retaining reasonable accuracy, optimization of the outer mold line can be significantly more efficient. Better optimization of the autoencoder can be achieved by using different model architectures and model parameters, or even by using alternative methods to an autoencoder such as generative adversarial networks. Based on my results, different model architectures and techniques should be looked into, as well as finding the best way to determine prediction error and be more accurate for values at lower heights. Also, by incorporating perceived loudness error directly into the autoencoder model, or by using the shape of the curves as an error metric, there lies the possibility of producing more accurate profile predictions. After the autoencoder is capable of producing an accurate representation of the original profiles, the next step is to use the compressed representation of profiles, which is done by removing the first part of the autoencoder, to then create arbitrary and feasible profiles that can be used in optimization. This enables less time-consuming optimization of the outer moldline of the aircraft with respect to most, if not all, possible atmospheric conditions. I would like to once again say thank you to all of the sponsors and collaborators, and I hope you enjoyed the presentation. Thank you.